This integral, or a very similar one, you found in your last mymathlab homework. It was the last question. An improper integral was given and asked whether it was convergent, divergent, and why. Nicely enough of mymathlab, you were also given a few integrals to compare to. So it already told you should decide by using a comparison test. And as a service, it gave you the integrals to compare to, which usually is something you would have to find yourself. So first, what does it mean for an integral to be convergent or divergent? These are terms you already know from limits, and there's a reason for that. Namely, in this integral you have to deal with an infinity. For t equals 0, we have 1 divided by 0, which would go to infinity. So we're integrating over a function that goes to infinity. And the question is, if I take the integral over all of that, will the area under this graph, will that be a finite or an infinite thing? Same if I integrate from minus infinity to a point, or from a point to plus infinity, or all the way from minus infinity to plus infinity. Is the integral exploding, or is it still a number? Whenever it's a number, we say it's convergent. Whenever it's exploding to plus or minus infinity, we say it's divergent. So how do we take care of infinities? I write down how we define such an integral. That is, instead of going to 0 where this is not defined, because we have 1 divided by 0, we go as close to 0 as possible and take the limit. This is what limits are good for, taking care of infinite stuff. So let's call this new lower bound a, and we come from the right side, so limit a to 0 from the right. And now the lower bound is a, the upper one is still pi divided by 2 of this integral. This is just copying if you can't read it. Sine 2t dt. And now we can compute this limit, and if it exists, the limit is convergent, and therefore the improper integral is convergent if this limit goes to plus or minus infinity. If it does not exist, if it diverges, this integral diverges. So if you get such a question, you could start just trying to compute the limit. That could be a bit difficult in such a case. And then you have a comparison criteria as another way of doing that. How does a comparison criteria work? That works as follows. I want to know whether or not I fit into a pair of trousers. If I know that I have a friend who is much smaller than me and already cannot fit into these trousers because they're just way too tight, I don't have to order them. I don't have to try myself. So that is if something is divergent, so it doesn't fit, and I'm even bigger than that. That's me. Well, that will be divergent as well. If I'm smaller than my friend, and I know my friend doesn't fit the pants, it doesn't tell me whether or not I will fit in the pants. So no conclusion. But if I know that my friend who is much bigger than me and can fit into the pants, so that is convergent, then for sure I can fit into the same pants. Maybe it's not your best choice of fashion, but for sure you will fit. So if I have something that's bigger and convergent, I can make a conclusion that the smaller thing is also convergent. If I have something that is divergent and smaller than myself, so plus infinity, then I know that I'm also going to plus infinity. And same if I have something that is, if that is minus infinity here, if I'm always smaller than something that is going to minus infinity already, then I also know that I'm going to minus infinity. So if I'm smaller than something that is going to minus infinity, well, for sure, I'm also going to minus infinity. So from here, divergent to minus infinity, also divergent to minus infinity follows. Now we're using such a comparison argument to show that this integral is either bigger than one of these, of whom we know already that it's exploding, or we show that it's smaller than one of these, for which we know that it's converging. How to choose these? In principle, that could be anything, but we have one class of integrals which are very useful to have in mind because they often work. They also work here, which are called the P integrals. You have them in your book. And that is 1 over x, if the variable is x. And here is a starting point for anything from 1 to infinity. The integral diverges. That's actually infinite. For everything from here to here, it's symmetry. This is the same, so that's also divergent. But this is exactly the boundary for convergency and divergency, in a sense that if I have a power that is higher than 1 and positive, for example, 1 divided by x to the power of 2, this is converging. That's actually a finite area. So everything that's below 1 divided by x here is converging, if it's such a form, a P integral. And everything that's above it, as here. So the symmetric thing would be anything above it. That is diverging by a comparison argument. It's bigger than something that already diverges. Something that's bigger than something that's infinite is for sure also infinite. So the integral of 1 over x squared from 0 to any point will diverge, but the integral from any point to infinity by 1 over x squared will converge. And same thing, other way around. If we take 1 over x a half, any positive exponent that is smaller than 1, so that would be square root of x, we have the symmetric situation. Here it's converging between 0 and any point, but the integral is diverging if taken from a point to infinity. So I just said this thing is 0 to pi half 1 over t. That is diverging. This thing is, well, there's only a factor of 11 and the square root that doesn't do anything to it, so that is converging. Now you need to know that these two are diverging. And now we hope to find that this one is either bigger than one of the diverging ones or it's smaller than the converging one. And these are diverging to plus infinity, plus infinity, plus infinity. So that's why we want it to be bigger. I'm not considering negative numbers. I don't have to because I know these are all positive numbers in here. These two summands are always positive on 0 to pi half. And if I add a positive thing in a denominator, the whole thing will become smaller, right? So that means this integral, I call it star, is definitely smaller than this. It's smaller than this. It's smaller than this. It's also smaller than that. So here I probably should also say that the square root only makes it even smaller. So now I know it's smaller than something that diverges in these three cases, so that doesn't help me. Just because my bigger friend doesn't fit into the trousers, it doesn't tell me whether I will or not. But this one tells me that a bigger thing already fits. So for sure I also fit. And that gives us that we should compare to 1 divided by square root of t. So we're comparing to this, where something that is whatever it looks like is smaller than this. So for sure it's also converging. And we have a conclusion together with the argument.